Out beyond the familiar dance of planets, past the orbit of Neptune and even Pluto, lies a region so vast and dark it defies comprehension. This is the Kuiper Belt, a sprawling frontier of icy worlds and cosmic relics left over from the birth of our solar system, a place where sunlight is little more than a faint, distant memory. Among these shadowy wanderers, one stands out not for its size or brightness, but for the profound mysteries it holds, a world named Varuna. Discovered just over 2 decades ago, Varuna immediately captured the imagination of astronomers not as just another rock in the dark, but as a puzzle box waiting to be opened, a celestial anomaly that whispers secrets about how planetary systems form and evolve. It's a place so strange that it doesn't just ask questions, it rewrites them. When we look at Varuna, we're not just looking at a distant object, we're looking back in time. This enigmatic world is a fossil preserved in the deep freeze of space, carrying with it clues about the violent, chaotic processes that shaped our solar system more than 4.5 billion years ago. Its unusual shape, its puzzling rotation, the very nature of its surface and composition, all of it challenges what we thought we knew about how planets come to be. And perhaps most intriguing of all, Varuna seems to exist in a category of its own, defying easy classification and raising the possibility that there are entire classes of worlds out there that we haven't even begun to understand. Every time we point our telescopes toward it, we're met with more questions than answers, and that's exactly what makes it so compelling. So what are the secrets Varuna is hiding? What can this distant, dark world teach us about the history of our cosmic neighborhood, and maybe even about the possibilities for life or strange phenomena in the coldest, most remote corners of space? In this video, we're going to explore the 25 most baffling, thrilling, and utterly unresolved mysteries surrounding Varuna, from its origins and structure to the unanswered questions that keep scientists up at night. This isn't just a tour of facts and figures, it's a journey to the edge of human knowledge, a chance to stand beside researchers as they grapple with the unknown. So settle in, open your mind to the wonders of the cosmos, and let's venture together into the deep. Our first great mystery begins not with what Varuna is, but with where it goes. Unlike the relatively placid, near-circular orbits of planets closer to the Sun, Varuna's path through space is a dramatic, stretched-out ellipse, a cosmic roller coaster that takes it on a wild journey from the inner fringe of the Kuiper Belt all the way out into the profound loneliness of the scattered disk. At its closest approach, it's still an incredible 40 astronomical units from the Sun, which is 40 times the distance from Earth to our star. But at the far end of its sweeping 280-year-long orbit, it ventures more than 100 astronomical units out into the void. To put that into perspective, at its most distant, Varuna is so far away that the Sun would appear as little more than an exceptionally bright star in its black sky, and a full day there would last less than one of our hours. This extreme eccentricity is a colossal puzzle because it defies the typical patterns we see in the Kuiper Belt. Most objects out there have settled into more stable, less elongated paths over the billions of years since the solar system formed. So the question is, what gave Varuna such a gravitational kick? One compelling theory points to the lingering influence of Neptune's migration in the early solar system. As the giant planet slowly drifted outward, its immense gravity could have acted like a slingshot, flinging primordial objects like Varuna into these strange, stretched orbits. It's a process known as gravitational scattering, and it would have been a hallmark of the solar system's violent youth. Yet there's an even more tantalizing possibility: the influence of forces we have yet to directly observe. Could the gravitational tug of a yet undiscovered planet, a so-called Planet 9 or Planet X, lurking in the extreme outer darkness, be shepherding Varuna and other objects into these peculiar paths? The mathematics of orbital dynamics suggests it's plausible, making Varuna's journey a potential piece of evidence in one of astronomy's greatest modern detective stories. Alternatively, some scientists have proposed that a rogue star, passing incredibly close to our infant solar system billions of years ago, could have stirred up the outer regions, leaving behind a legacy of chaos in the form of orbits just like Varuna's. This unpredictable path has profound consequences for the world itself. As it plunges inward and soars back outward, Varuna experiences staggering variations in temperature. This constant thermal flexing, a cycle of deep freeze and relative thaw repeated over centuries, likely plays a major role in any geological activity on its surface, perhaps causing its icy crust to fracture and renew itself in ways we are only beginning to model. Its eccentricity isn't just an orbital statistic, it's the defining force shaping the conditions on this remote and enigmatic world. While its orbit sets the stage, the next enigma lies in Varuna's very motion, a dizzying, relentless spin that defies all expectations for an object of its size. This world completes a full rotation in just about 6 hours and 20 minutes, a blink of an eye in cosmic terms. To put that into perspective, that's faster than Earth, faster than Mars, and even faster than the larger, more massive dwarf planet Pluto. In fact, Varuna spins so rapidly that it ranks among the very fastest rotating large bodies we've found in the entire solar system, a true outlier whirling in the silent dark. Such a frantic rotation rate immediately presents a colossal puzzle for planetary scientists. The standard model of how objects form, through the gradual, gentle accumulation of material in the early solar nebula, typically results in much more sedate spins. Think of it like an ice skater pulling their arms in to spin faster. As a forming planetesimal gathers material, its rotation should naturally increase. But there's a limit. If it spins too fast during its formation, the centrifugal force would simply prevent any more material from accreting, stopping it from growing larger. So how did Varuna, a body estimated to be over 600 kilometers in diameter, end up spinning at a rate that should have prevented it from ever reaching that size? This fundamental contradiction suggests that its current state isn't a relic of its birth, but rather the result of a dramatic, violent event that occurred long after it formed. The most compelling explanation points to a cataclysmic collision in the deep past. Imagine another sizable Kuiper Belt object, perhaps hundreds of kilometers across, slamming into a primordial Varuna in a colossal, slow-motion impact. The transfer of energy from such an event could have acted like a cosmic hammer strike, dramatically accelerating its rotation and setting it spinning for eons to come. This isn't just speculation. We see evidence of similar giant impacts throughout the solar system. The most famous example is Uranus, which orbits the Sun tipped over on its side, believed to be the result of a planet-shattering collision. Earth's own moon is thought to have been born from the debris of a giant impact with a Mars-sized protoplanet. For Varuna, a similar violent encounter could be the key to unlocking its secret. This rapid spin has profound and ongoing consequences for the world's very structure. The tremendous centrifugal force generated by spinning that fast would significantly flatten the body, distorting it from a sphere into a more elongated, watermelon-like shape. This constant stress places immense strain on its internal composition, which is likely a mix of rock and various ices. The question of whether its gravity is even strong enough to pull it into a relaxed, rounded shape, a state known as hydrostatic equilibrium that defines a dwarf planet, remains an open and hotly debated question, directly tied to this frantic rotation. Furthermore, this non-stop motion likely makes Varuna a geologically active world, but not in any familiar sense. The constant flexing and stress could generate internal friction, potentially warming its interior enough to maintain a subsurface layer of slushy, viscous ice or even a hidden ocean of ammonia-rich water deep below the surface. This internal heat could in turn drive cryovolcanism, where slushy ice mixtures erupt from fractures in the crust, constantly renewing and reshaping its ancient surface. The rapid rotation also means its days are incredibly short, with the sun racing across the sky, leading to extreme temperature swings between its brief days and equally brief nights, further fracturing and weathering the landscape. Varuna's spin isn't just a curious fact, it is the engine that drives its entire evolution, a relentless force sculpting a world of mystery millions of miles from the sun. The mystery deepens as we turn from Varuna's dramatic motion to the very nature of its skin, a surface so profoundly dark it challenges our expectations of what an icy world should be. Out in the freezing depths of the Kuiper Belt, where sunlight is already 1,000 times weaker than on Earth, most objects are covered in highly reflective ices that act like cosmic mirrors, bouncing back a significant portion of that feeble light. Pluto, for instance, has a relatively bright surface with an albedo or reflectivity of around 50 to 60%. But Varuna is different. It is a shadowy ghost, absorbing most of the light that touches it and reflecting back a mere 12 to 20%, making its surface darker than fresh asphalt and among the darkest landscapes we know of in the outer solar system. This profound darkness isn't just a curious feature, it's a direct window into the complex and ancient chemistry occurring in the deep freeze of space. So what could coat a world in such a deep, light-absorbing blanket? One of the leading theories points to the long-term effects of cosmic radiation. For billions of years, Varuna's surface ices, primarily a mix of water, methane, and nitrogen, have been bombarded by a relentless hail of high-energy particles from the sun and from deep space. This radiation acts like a cosmic chef, slowly cooking these simple ices and breaking apart their molecular structures. Over eons, this process, known as radiolysis, can transform simple frozen methane into long, complex chains of carbon-rich molecules called tholins. These tholins are not a single substance but a class of sticky, organic polymers that are notoriously dark red or nearly black in color. They are essentially the same kind of complex gunk that gives other distant worlds, like Saturn's moon Iapetus or Pluto's darker regions, their distinctive coloration. On Varuna, a constant rain of radiation could have built up a thick, global layer of this dark organic sludge, effectively painting the entire world a deep, light-absorbing hue. Another compelling idea suggests that Varuna's darkness isn't something that developed over time, but is instead an intrinsic, primordial characteristic. Perhaps this world formed from some of the original, unprocessed building blocks of the solar system, material that was already naturally dark. In the earliest days of the protoplanetary disk before the planets coalesced, there would have been abundant amounts of dark, carbon-rich dust and complex organic compounds swirling among the ices and rocks. If Varuna accreted quickly from a region rich in this primordial soot, its very foundation could be dark from the inside out. Its surface would then simply be a reflection of its internal composition, a fossilized snapshot of the dusty ingredients that were available in its specific neighborhood over 4 billion years ago. This would make it less of an actively evolved world and more of a preserved relic, a time capsule showing us the raw, dark materials from which larger worlds were built. There's also a more dynamic possibility that ongoing geological processes are actively renewing and darkening its surface. Varuna's rapid spin and eccentric orbit create significant tidal and rotational stresses that could be driving cryovolcanic activity. If slushy, warm material from a potentially warmer interior were to well up and erupt onto the surface, it would initially be brighter. But exposed directly to the harsh space environment, these fresh ices would be rapidly darkened by radiation. This would create a continuous cycle where new ice is laid down only to be quickly tarred over, maintaining a consistently low albedo across the globe. It's a fascinating feedback loop where internal activity and external space weather work in tandem to keep the world shrouded in darkness. This profound lack of reflectivity has a direct and measurable consequence. It makes determining Varuna's true size an incredibly difficult task for astronomers. We can't simply measure how bright it appears and calculate its diameter. A large, dark object can look identical to a small, bright one in a telescope. This is why initial size estimates for Varuna have varied so wildly, and why its classification as a potential dwarf planet remains hotly debated. Its darkness is literally obscuring our view of its physical stature. Furthermore, a dark surface absorbs more energy from the scant sunlight available. This could lead to surprisingly complex thermal dynamics on its surface, with the potential for slight warming that might trigger the sublimation of more volatile ices, perhaps even creating a transient, ultra-thin atmosphere that itself could contribute to further darkening processes through the deposition of new compounds. The simple fact of its dark surface is therefore a master key, unlocking questions about its composition, its history, its internal activity, and its very identity within our solar system's family. This profound darkness leads us directly to our next great puzzle, a question that seems to defy basic planetary science. Where is Varuna's atmosphere? Given its substantial size and a composition rich in volatile ices like methane and nitrogen, the very same ingredients that give Pluto and Neptune's moon Triton their complex, hazy skies, we would fully expect Varuna to sport at least a temporary shroud of gas. Especially when it makes its closest approach to the Sun, the slight increase in solar energy should be enough to trigger a dramatic process called sublimation, where surface ices turn directly into gas without ever becoming liquid. Yet, despite our most sensitive searches using the world's largest telescopes and most advanced instrumentation, no atmosphere has been definitively detected. This isn't just a minor discrepancy, it's a glaring absence that forces us to reconsider the fundamental rules of how small, icy worlds behave in the outer solar system. One of the most straightforward explanations could be Varuna's sheer distance from the Sun. Even at its perihelion, the closest point in its orbit, it remains an incredibly remote 40 astronomical units away. At that range, the sunlight it receives is pathetically weak, a mere 1/1600th of the solar energy that reaches Earth. This feeble warmth might simply be insufficient to heat the surface enough to sublimate a significant amount of ice into gas. The ices on its surface could be so cold, so deeply frozen, that they behave more like inert rock than potential atmospheric fuel. However, this theory runs into a problem when we look at other, similar-sized Kuiper Belt objects. Some, like the dwarf planet Makemake, are known to have tenuous but detectable atmospheres, and they occupy a similar frigid realm. So if they can do it, why can't Varuna? This suggests that distance alone isn't the full answer, and that something more unique is at play on this particular world. This brings us to a far more compelling possibility. Varuna's atmosphere might be a transient, ghostly presence that appears and vanishes in a cycle we haven't yet been lucky enough to catch. Its wildly eccentric orbit means the conditions on its surface change dramatically over its 280-year journey around the Sun. The window of time when it is close enough to the Sun for significant sublimation to occur might be incredibly narrow, perhaps lasting only a few decades out of its entire long orbital period. Our telescopes have only been trained on it for a tiny fraction of that cycle, a mere blink in its long year. It's entirely possible that we've been looking during its long, dormant winter, when any atmosphere has long since frozen back onto the surface as a fresh layer of frost. We might simply need to wait and watch, hoping to catch it during its brief summer when it briefly comes to life. Yet another theory points to the composition of the ices themselves. Not all ice sublimes at the same rate or under the same conditions. If Varuna's surface is predominantly water ice, which has an extremely low vapor pressure at those temperatures, it would be effectively locked in place, refusing to turn to gas. Any more volatile ices like methane or nitrogen could be buried beneath this resilient water ice crust, shielded from the sun's weak rays and unable to escape. Alternatively, that dark, complex layer of tholins we discussed could be acting as a kind of cosmic insulating blanket. This dark, tar-like material would absorb the sun's heat, but instead of transferring it downward to sublimate the ices below, it might simply re-radiate that energy back into space, preventing the subsurface from ever getting warm enough to produce any gas. The surface itself could be effectively sealed, trapping its volatile materials inside. Then there is the brutal physics of atmospheric escape. Varuna's relatively low gravity, a consequence of its modest mass, would have a very weak hold on any gas molecules that do manage to break free from the surface. In the vacuum of space, these molecules would zip around at high speeds, and any that reached a certain velocity would easily achieve escape velocity, flying off into interplanetary space never to return. This process could be so efficient that any atmosphere that tries to form is stripped away almost instantly, creating a continuous leak that the world simply cannot replenish fast enough. The solar wind, a stream of charged particles constantly flowing from the sun, would also relentlessly buffet and erode any tenuous atmosphere, sputtering it away atom by atom over time. Finally, we must confront the very real possibility that our current technology is simply not yet sensitive enough to detect what is there. Varuna's atmosphere might not be a grand global envelope like Titan's, but rather an ultra-thin, localized or seasonal haze. Our primary method for detecting these distant atmospheres involves watching as the object passes in front of a distant star, an event known as a stellar occultation. If an atmosphere is present, it will cause the star to dim in a very specific, gradual way just before and after the main body blocks its light. But these events are incredibly brief and difficult to observe with perfect precision. A very thin atmosphere might produce a signature so subtle that it gets lost in the noise of our observations. The next generation of telescopes, like the James Webb Space Telescope with its incredible infrared sensitivity, might hold the key. It could be capable of sniffing out the spectral fingerprints of minute amounts of gas surrounding Varuna, finally solving the mystery of its missing sky and revealing whether it is a truly airless tomb or a world with breaths too faint for us to yet perceive. But the enigma of Varuna's missing atmosphere is only the prelude to an even more baffling observational puzzle, one that astronomers have been grappling with since its discovery: its inexplicable and unpredictable changes in brightness. Like a distant cosmic lighthouse with a faulty mechanism, Varuna's light curve, the graph that charts its brightness over time, does not behave as it should. For a solitary, rotating world, we expect a rhythmic, predictable pattern. The brightness should rise and fall with perfect regularity, corresponding to its 6.3-hour rotation period as different sides, perhaps with slightly varied terrain, turn toward Earth. Yet Varuna's light curve is messy, complex, and inconsistent. The peaks and troughs of its brightness shift in both magnitude and timing, sometimes deepening dramatically and at other times almost flattening out. This isn't just random noise, it's a clear signal that something highly unusual is happening on or around this distant world, something that defies a simple explanation. The most straightforward theory to explain these variations points to an incredibly heterogeneous surface, a landscape of stark extremes. Imagine a world not of subtle shading, but of dramatic contrasts, vast plains of pitch black, radiation-darkened tholins sitting right beside brilliant, freshly exposed cliffs of gleaming water ice. As Varuna spins, these vastly different terrains would rotate into and out of our view. A large, dark region turning toward Earth would cause a significant dip in the overall brightness, while a highly reflective icy plain would create a pronounced peak. The irregular shape of the world, likely elongated by its rapid rotation, would amplify this effect. The changing cross-section presented to us as it tumbles through space would combine with these surface variations to create a complex, shifting pattern of light that never quite repeats itself exactly. This would paint a picture of a geologically active and diverse world, one whose surface is a patchwork quilt of ancient darkness and startling renewal. However, the peculiarities of the light curve have led some scientists to propose an even more dramatic explanation: the presence of enormous geological features that sculpt light and shadow on a grand scale. A single, colossal impact crater spanning hundreds of kilometers across could be the culprit. As the crater basin rotates toward the observer, its deep interior would be cast in profound shadow, creating a sharp and sudden drop in brightness. Conversely, when the towering rim of the crater catches the faint sunlight, it could create a bright, glinting peak. Alternatively, a massive mountain range or a series of deep, canyon-like fractures could produce similar effects, their topography creating complex patterns of light and shadow that change with the angle of illumination and our perspective from Earth. This would suggest a world that has undergone titanic forces, bearing the scars of a violent and dynamic history written across its face in light and dark. But the most tantalizing and exotic theory moves beyond the surface of Varuna itself to propose a dynamic, ephemeral environment surrounding it. The irregular brightness dips could be caused by a transient, incomplete ring system or a localized cloud of debris, fine dust and icy particles lofted from the surface by recent impacts or even by cryovolcanic outbursts. This material would not form a uniform ring like Saturn's. Instead, it might exist in dense, clumpy arcs or a thin, uneven haze. As this debris field orbits Varuna, it would periodically pass between the world and our telescopes, partially obscuring our view and causing those unexplained, non-periodic dimming events. This would make Varuna a far more dynamic system than a simple, solitary rock, instead resembling a miniature planetary system with its own cloud of satellites and dust, a concept we've seen with other centaurs and Kuiper Belt objects like the ringed dwarf planet Haumea. There's also a fascinating temporal aspect to consider. Varuna's extreme orbit subjects it to wild temperature swings. When it is near perihelion, the slight warming could be enough to trigger the sublimation of the most volatile ices on its surface, like nitrogen or carbon monoxide. This process could create temporary, localized patches of frost that are highly reflective. These bright spots would appear, change shape, and vanish over timescales that don't align with the rigid rotation period, directly influencing the light curve in unpredictable ways. We could be witnessing the real-time weathering and changing face of a distant world, a cycle of frost and exposure that plays out over decades, not hours. Each observation of Varuna might be capturing a unique snapshot in this ongoing seasonal cycle, making its light curve a living record of its interaction with the sun. Ultimately, cracking this photometric code is paramount because the light curve is our primary tool for understanding this distant object. Its irregularities hold the key to determining its true shape, rotation period, and even the orientation of its pole. Until we can fully model and explain why its brightness changes so oddly every other measurement we take, its size, its density, its albedo carries a significant margin of error. The mysterious flickering of this distant world is more than just an academic curiosity. It is the biggest obstacle standing between us and a true understanding of Varuna's nature, a cryptic signal from the dark that we are only just beginning to decipher. Yet for all the mysteries written in its light, the most fundamental question about any world remains: what is it made of? This brings us to a deep and contradictory puzzle at the heart of Varuna, one that strikes at the very core of its identity, the paradox of its density. For an object we cannot even touch or see clearly, density is a critical number. It's the cosmic fingerprint that tells us the ratio of rock to ice, of empty space to solid matter, and it dictates everything from internal structure to geological potential. And for Varuna, this number is a source of profound confusion. Estimates from different studies and models have produced values that are not just slightly off. They are wildly, bafflingly contradictory, ranging from a feather-light 0.992 grams per cubic centimeter to a surprisingly dense 1.5 or even higher. To grasp why this is so strange, consider what those numbers mean. The lower estimate suggests an object lighter than pure water ice, a world that would literally float if you could somehow drop it into a colossal planetary-sized ocean. The higher estimate points to a body made of nearly half rock, a much more substantial and planet-like composition. This isn't a minor margin of error, it's a chasm of uncertainty that forces us to question whether we understand this world at all. The root of this paradox lies in the immense difficulty of measuring two basic properties from 4.5 billion miles away, mass and volume. To calculate density, you simply divide an object's mass by its volume. For a distant Kuiper Belt object, both of these numbers are incredibly hard to pin down. Let's start with volume. Determining Varuna's size is a challenge because, as we've discussed, its surface is so dark and its shape is almost certainly not a perfect sphere. We rely on combining data from its observed brightness with thermal emissions detected in the infrared. But if our models for its albedo are wrong, or if we misunderstand how its irregular shape and rapid rotation affect how it absorbs and re-radiates heat, our size estimate can be significantly off by tens of kilometers. A larger estimated size with the same assumed mass would give a lower density. A smaller estimated size would give a higher one. Our view of its physical dimensions is still frustratingly blurry. The challenge of measuring its mass is even more formidable. For planets, we can watch how they gravitationally influence their moons or nearby spacecraft. Varuna has no known moons, so astronomers must use a far more subtle technique, analyzing how it minutely perturbs the orbits of other, smaller objects in its vicinity over decades. This requires painstakingly precise tracking of countless tiny rocks across the vastness of the Kuiper Belt, looking for the faintest gravitational signature of Varuna's influence. It's an astronomical detective story of the highest order, and the results are still tentative. A small error in the mass calculation, combined with an error in the volume, creates a compounded and enormous uncertainty in the final density figure. We are, in effect, trying to weigh a distant, tumbling, irregularly shaped object by watching how it makes other tiny, distant, and also tumbling objects wobble almost imperceptibly. If the higher density estimates are correct, it paints a picture of a highly differentiated and complex world. A density over 1.5 grams per cubic centimeter would suggest that Varuna underwent significant internal heating early in its history. This warmth, perhaps generated by the decay of radioactive isotopes like aluminum-26, would have been enough to melt its interior. In this molten state, the heavy, dense rocky material would have sunk inward, forming a substantial solid core, while the lighter ice's water, methane, ammonia would have risen to form a thick mantle and crust. This process of differentiation is what creates the layered interiors of planets like Earth. It would mean Varuna isn't just a simple, primordial ball of dirty ice. It's a geologically evolved mini-world with a complex inner structure that could potentially power cryovolcanism or even sustain a subsurface ocean to this day, locked deep beneath the ice. Conversely, if the lower density estimates hold true, the implications are even more staggering. A density below 1 gram per cubic centimeter is extraordinarily low for a solid body. It suggests an object that is incredibly porous, like a cosmic sponge or a loose pile of rubble barely held together by its own gravity. This could mean that Varuna is not a single, solid monolith but a rubble pile object, a collection of smaller rocks and ice chunks that were gently gathered by gravity after an ancient, catastrophic collision that shattered a larger progenitor body. The tremendous voids and empty spaces between these chunks would account for the surprisingly low overall density. This would make it a fragile world, one that might deform dramatically under its own rapid spin, and its internal structure would be a chaotic jumble rather than a neat series of layers. Any significant impact could potentially disrupt it entirely. There is a third, even more exotic possibility that could resolve the paradox: a hybrid model. Perhaps Varuna does have a dense, rocky core, but it is also highly porous. The porosity wouldn't be uniform. The intense pressure at the center would crush any voids, creating a solid core. But further out, in the mantle and crust, the material could be exceedingly porous and fractured. This would create an average density that falls somewhere in the middle of the extreme estimates, a number that reflects a mix of very dense and very light material. This model is particularly appealing because it could reconcile the conflicting data. It suggests a world that was both heated enough to differentiate and battered enough by impacts to be shattered and reassembled into a fragile, porous structure. Until we can send a spacecraft to Varuna to measure its gravity field directly, this density paradox will remain one of the most fundamental and unresolved questions about its true nature, a simple number that holds the key to unlocking billions of years of hidden history. This relentless, dizzying spin that we just discussed doesn't just influence Varuna's internal dynamics. It actively sculpts its very form, warping it into a shape that may defy our very definition of a world. The most widely accepted model for its shape is perhaps its most striking visual mystery, that of a scalene ellipsoid, a distorted, watermelon-like form stretched along its equator by centrifugal force. Imagine a cosmic lump of clay spinning on a potter's wheel at an incredible rate. The material at its middle wants to fly outward, flattening the poles and bulging the equator. For Varuna, with its 6.3-hour rotation, this force is so powerful that it may have prevented the world from ever collapsing into the relaxed, spherical shape of hydrostatic equilibrium, the key criterion for being classified as a dwarf planet. Instead of a sphere, we could be looking at a triaxial ellipsoid, a world with 3 different axes, a long one, a shorter one, and an even shorter one, making it look something like a rounded-off football or a massive tumbling potato. The evidence for this bizarre morphology is etched into its light curve. The changes in its brightness are simply too extreme to be explained by surface features alone on a perfectly spherical body. The variations require an object that presents a dramatically changing cross-sectional area to Earth as it rotates. An elongated shape does this perfectly. As it spins end over end, we see the long, skinny side, which appears fainter, and then the broader, short side, which appears significantly brighter. This fits the observed data far better than a simple sphere with dark and light patches ever could. It's a compelling solution, but it raises a host of new questions about the physical strength and history of this distant object. Such a distorted shape speaks volumes about Varuna's internal composition and mechanical properties. A body made of solid, strong rock would resist this kind of deformation. Its internal strength would fight the centrifugal force and maintain a more spherical form. The fact that Varuna appears to have yielded so completely to the rotational stress suggests that its interior is relatively weak and malleable. This supports the idea that it is a rubble pile object, a collection of smaller rocks and icy chunks held together by gravity rather than a monolithic solid sphere. Think of it not as a single, solid billiard ball, but as a gigantic, self-gravitating bag of loosely packed sand and ice. This kind of structure has very little internal strength, allowing the entire aggregate to be easily molded by the relentless spin into its current, elongated configuration. It's a world built not on a foundation of stone, but on a framework of gravity alone. This leads directly to the contentious debate over its classification. The International Astronomical Union defines a dwarf planet as a body that orbits the Sun, is not a moon, and has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatically equilibrium shape, meaning it becomes roughly round. This is the line that separates complex, planet-like worlds from simple, irregular asteroids. Pluto, Eris, and Haumea all meet this criterion, even Haumea with its own elongated, rugby ball shape caused by rapid rotation. Its gravity was still strong enough to pull it into a state of equilibrium, just a distorted one. Varuna, however, may be sitting right on this crucial boundary. If its gravity was not quite strong enough to pull it into any equilibrium shape, if it remains an irregular, distorted ellipsoid held that way by its spin rather than relaxed into that form by its gravity, then it may not qualify as a dwarf planet. It would instead be a very large trans-Neptunian object, a magnificent and fascinating world that simply didn't make the cut for planetary status, revealing just how fine and perhaps arbitrary the line can be between different classes of solar system bodies. The possibility of a violent collisional history adds another layer of intrigue to its form. That rapid rotation, as we explored, is almost certainly the result of a giant impact. Such a cataclysmic event wouldn't have just set it spinning, it could have literally knocked it into shape. The impactor might have delivered a tremendous off-center blow that shattered a more spherical progenitor and sent the debris flying. What recoalesced from that chaos could have been the elongated, rapidly spinning Varuna we infer today. The shape, therefore, might not be solely the product of its current spin, but also a fossilized relic of the most violent day in its long history, a permanent scar from a collision that occurred when the solar system was still in its infancy. Understanding Varuna's true shape is about more than just categorizing it. It's a fundamental test of our models for how mid-sized icy bodies behave under stress across the solar system. It probes the limits of material strength and gravitational dominance in the frigid outer darkness. Is there a size threshold where gravity always wins and makes objects round, or can factors like rotation rate and formation history create permanent, stable exceptions? Varuna appears to be that exception, a crucial data point showing that even objects several hundred kilometers across can retain profoundly irregular shapes, challenging our tidy classifications and forcing us to appreciate the beautiful, chaotic diversity of worlds on the frontier of our solar system. Just when we thought we had begun to map the boundaries of Varuna's strangeness, we are confronted with a thermal puzzle that seems to defy the very laws of physics as they apply in the outer solar system. From the freezing darkness, some 4.5 billion miles from the Sun, we would expect a world to be little more than a nearly absolute zero tomb, a place where all internal heat has long since bled away into the vacuum of space. Yet, detailed infrared observations reveal something startling. Varuna appears to be warmer than it has any right to be. Its thermal emissions are subtly but consistently higher than what our most careful models predict for an object of its size and distance, a discrepancy that points to the presence of an active internal heat source. This is not just a minor calibration error, it is a thermal anomaly that suggests Varuna is not the dead, frozen relic we presumed it to be, but a world with a hidden, warm heart beating slowly beneath its icy crust. The most foundational source of heat for any rocky body is the decay of radioactive isotopes locked within its interior. Elements like potassium-40, thorium-232, and uranium-238 have half-lives measured in billions of years, meaning they are still actively breaking down and releasing energy in the form of heat. For a large planet like Earth, this radiogenic heating is a powerful driver of plate tectonics and volcanism. But for a smaller world like Varuna, the math has always been tricky. Its relatively modest volume means it contains a much smaller inventory of these radioactive elements, and its large surface area to volume ratio should allow that meager heat to radiate away into space quite efficiently. For it to retain enough of this heat to create a measurable anomaly at the surface, its interior would need to be exceptionally well insulated. This could be possible if its hypothesized porous rubble pile structure acts as a fantastic thermal blanket. The countless tiny air gaps between the chunks of rock and ice would be superb insulators, trapping the feeble warmth from radioactive decay and allowing it to build up over eons, slowly warming the interior like a thermos flask holding heat in the deep freeze of space. Another captivating possibility is that Varuna is, or once was, a beneficiary of tidal heating. This is the process that keeps the interiors of moons like Jupiter's Io and Europa molten, generated by the constant gravitational flexing they endure from their massive parent planet. Varuna has no such giant planet tugging on it today, but its past could tell a different story. During the early chaotic days of the solar system's formation, when the orbits of the giant planets were still migrating outward, it is entirely possible that Varuna was once much closer to Neptune. If its orbit brought it into a temporary gravitational resonance with the ice giant, even for a short period, the resulting tidal forces could have pumped a tremendous amount of energy into its interior, heating it up dramatically. Although that intimate dance ended long ago as Neptune moved away, the heat from that brief, violent encounter could have been partially retained, especially if, again, its porous structure locked that energy in. It's a fossil heat, a memory of a passionate gravitational affair from billions of years ago that still keeps the world warm. There is also the profound concept of accretion heat to consider. The energy released when countless planetesimals slammed together to form Varuna would have been immense, essentially cooking the forming world from the inside out. In most models, this heat is thought to have dissipated relatively quickly for smaller objects, but Varuna's unique composition might have changed that equation. If its interior is rich in certain types of clathrate hydrates icy cages that can trap gases like methane or argon, these structures could have acted as a kind of chemical capacitor for heat. Alternatively, if its material included a larger than expected amount of amorphous ice, a non-crystalline form of water ice that forms in the extreme cold, the gradual transition of this ice to a more stable crystalline state over billions of years releases a significant amount of latent heat. This slow, relentless exothermic process could provide a gentle but persistent warming from within, a constant, low-level energy source that has been operating since the world's birth. This internal warmth is not just an academic curiosity. It has dramatic implications for the potential habitability and geological activity of this distant world. The most thrilling possibility it raises is that of a subsurface ocean. We now know that such hidden seas are not the exclusive domain of large moons. The dwarf planet Ceres and Pluto are both suspected to harbor them. For Varuna, even a small amount of internal heat, combined with antifreeze compounds like ammonia likely present in its ice, could be enough to maintain a layer of liquid water deep beneath the surface. This would not be a vast, globe-spanning ocean, but perhaps a regional, sludge-like layer of briny water, a dark, pressurized aquifer where who knows what chemical processes might be unfolding in complete isolation for billions of years. This heat also provides the engine for ongoing geological activity. It could be the driving force behind the cryovolcanism we speculated about earlier, providing the energy to melt subsurface ices and push that slushy material up through fractures in the crust. This process would constantly renew the surface, covering old, dark terrain with fresh, bright ice, which would neatly explain the strange albedo variations and complex light curve we observe. The warmth could also be facilitating a slow, solid-state convection within the ice mantle, a lazy, churning motion that over millions of years reshapes the landscape from below, creating vast, icy tectonic features that we can only begin to imagine. The thermal anomaly is therefore the master key that could unlock almost every other mystery about Varuna. It suggests a world that is not static and dead, but dynamically alive in its own slow, cold way, a place where the faint, enduring pulse of internal heat writes an ongoing geological story on a canvas of ice and darkness. While internal heat provides a dynamic engine for Varuna, the true nature of its surface materials presents a separate enigma, one written not in temperature but in light. When astronomers point their spectrometers toward this distant world, they are not just measuring brightness, they are reading a complex chemical fingerprint, a spectrum that reveals the specific molecules present on its surface. And for Varuna, this spectral signature is deeply puzzling. It shows clear evidence of water ice, the bedrock of most outer solar system objects, but it also displays the unmistakable marks of methane and hints of nitrogen frost. This in itself isn't wholly unexpected. The real mystery lies in the specific proportions and the physical state of these ices, a mixture that is strikingly different from what we see on other similar-sized Kuiper Belt denizens like Quaoar or Makemake, suggesting Varuna's history is one of a traveler, a world that may not have formed in the placid region where it currently resides. The presence of methane ice is particularly telling. Methane is a highly volatile substance. At the temperatures found in the Kuiper Belt, it will slowly but surely sublimate directly from a solid into a gas and escape into space over millions of years. For it to still be present on Varuna's surface in detectable amounts means one of two things. Either this world is massive enough to have sufficient gravity to hold onto these lighter molecules, which current size estimates make questionable, or its methane is being continuously replenished from within. This points back to the possibility of internal geological activity, where cryovolcanic processes or convective overturn in the ice mantle are constantly bringing fresh, methane-rich material up to the surface, effectively recoating it and maintaining its spectral signature against the relentless erosion of space. Yet the plot thickens when we consider the physical state of these ices. The specific absorption features in Varuna's spectrum suggest that its water ice exists primarily in a crystalline form. This is significant because in the extreme cold and constant radiation bombardment of deep space, water ice should amorphize over time. Its orderly crystalline structure should be knocked into a disordered, glassy state. The fact that it remains crystalline is a strong indicator of recent resurfacing. Some process, whether tidal heating in the past, residual radiogenic warmth, or the energy from impacts, must have been sufficient to warm the ice enough to allow its molecules to reorganize back into a crystalline lattice, or to have buried the old, amorphous ice under a fresh crystalline layer. This paints a picture of a world that is not geologically static. The most captivating clue, however, comes from the tentative detection of nitrogen ice. Nitrogen is the most volatile ice of all, the dominant surface material on Pluto and Triton, but it is rarely seen on smaller Kuiper Belt objects. Its presence on Varuna, even in small amounts, is a major anomaly. Nitrogen requires incredibly cold conditions to remain stable as a surface ice for long periods. This implies that Varuna either formed in an even colder, more distant region of the primordial solar system, perhaps in the very fringes of the protoplanetary disk or even in the hypothesized Oort cloud, or that it has managed to preserve these ultra-volatile ices in a uniquely sheltered way, perhaps buried beneath a protective, insulating layer of darker tholins until recently exposed. This peculiar cocktail of ices forms the basis for a compelling narrative of migration. The standard model of solar system formation suggests that objects largely formed where we see them today, condensing from the solar nebula at temperatures corresponding to their distance from the Sun. Varuna's composition throws a wrench into this simple idea. It appears to be a hybrid bearing the chemical markers of multiple distinct formation environments. It may have originated much further out in the solar system, in a region cold and pristine enough to allow the accretion of nitrogen and methane right into its fundamental structure. Then, through the gravitational chaos of the early solar system, perhaps during the Great Migration of Neptune, it was scattered inward to its current position in the Kuiper Belt. Alternatively, it could be a local product that experienced a very different thermal history than its neighbors. If Varuna was involved in a giant impact early on, that cataclysm could have excavated deep, volatile, rich material from its interior and spread it across the surface, creating the unusual spectral mixture we see today. The compositional mysteries of its surface are therefore far more than a simple inventory of chemicals. They are a cryptic historical record, a testament to a violent and mobile past, suggesting that this world has journeyed across vast expanses of the solar system, collecting ices from different thermodynamic environments before settling into its present looping orbit, a silent witness. Turbulent dawn of our planetary family. The 10th great mystery surrounding Varuna is perhaps the most foundational of all. Where did it come from? This isn't just a question of its current address in the Kuiper Belt. It's a probe into the very origin story of this world, an investigation that forces us to rewind the clock over 4 billion years to the chaotic construction site of our solar system. The clues we've gathered from its orbit and its composition don't paint a simple, coherent picture. Instead, they present a jumble of evidence that supports several radically different and competing narratives, each one transforming Varuna from a simple ice ball into a potential traveler, an immigrant from a different part of our cosmic neighborhood, or perhaps even a refugee from an entirely different star. The most straightforward theory is the in situ formation model. This scenario suggests that Varuna formed pretty much right where we find it today, condensing from the primordial solar nebula in the cold, dark reaches beyond Neptune. In this story, it is a true native of the Kuiper Belt, a local product that has resided in this region for its entire existence. The evidence for this is its current membership in the dynamically hot population of the Kuiper Belt, objects with inclined and eccentric orbits like Varuna's. This population is thought to be relatively primordial, having formed in situ but having their orbits excited and stirred up by gravitational interactions, most likely with Neptune during its outward migration. Its compositional mix of water, methane, and nitrogen ices is also broadly consistent with what we'd expect from objects that formed in this cold region of the protoplanetary disk. This theory paints Varuna as a homebody, a world that has always lived in the deep freeze, its wild orbit merely a scar from the gravitational turmoil that shook the outer solar system in its youth. A second, and perhaps more compelling, theory casts Varuna in a more dynamic role, that of an immigrant scattered outward from a birthplace much closer to the Sun. This narrative is tied intimately to the grand tack model of planetary migration, which suggests the giant planets, particularly Neptune, formed much closer to the Sun before embarking on a grand journey outward. As Neptune migrated, its immense gravity would have acted like a cosmic shepherd, scattering a vast population of smaller icy bodies before it. Some were flung inward to become today's Jupiter family comets, while others, like Varuna, were kicked outward onto stable but eccentric orbits in the Kuiper Belt. This scenario elegantly explains the extreme eccentricity of Varuna's path. It's not an original feature but a badge of honor from a close encounter with a giant. Compositionally, this could also make sense. If Varuna formed between the orbits of Saturn and Neptune, it would have accreted in a slightly warmer environment, potentially explaining certain nuances in its ice chemistry that pure Kuiper Belt formation might not account for. In this story, Varuna is not a native but a settler, pushed out to the frontier by the expansion of the solar system's great powers. The most exotic and thrilling possibility is the capture scenario. This theory posits that Varuna did not form in our solar system at all, but is instead an interstellar object that was captured by the Sun's gravity during a close flyby in the distant past. We now know that such interstellar interlopers exist, with objects like Oumuamua and 2I/Borisov passing through our inner solar system. While these were small and on hyperbolic trajectories, the early Sun was born in a dense star cluster, surrounded by thousands of sibling stars in close proximity. In this stellar nursery, the gravitational pull of a passing star could have been strong enough to strip away a cloud of cometary bodies from its periphery, and for our Sun to capture some from another system in return. The evidence for this is admittedly thin and highly speculative, but it rests on Varuna's sheer strangeness. Its combination of rapid rotation, dark surface, peculiar ice mix, and extreme orbit could be interpreted as the signature of an object that formed under a completely different set of physical and chemical conditions around another star. Its orbital inclination could be a fossilized record of that foreign origin. While this is the least likely scenario, it remains a tantalizing, if remote, possibility that underscores just how mysterious this object truly is. It invites us to consider that we might be studying a permanent visitor from another part of the galaxy, a fossil world that carries the secrets of another star's planetary formation within its icy heart. Each of these origin stories leaves a distinct set of fingerprints, and astronomers are desperately searching for them in the data. The in situ formation model predicts that Varuna's composition should be a near-perfect match for other large, dynamically hot Kuiper Belt objects. The outward scattering model predicts subtle differences, perhaps a lower abundance of the most super-volatile ices like nitrogen, as a closer formation to the Sun might have prevented their incorporation. The capture model would be the hardest to prove, but a truly bizarre and unique isotopic ratio. For instance, in the deuterium to hydrogen ratio locked in its water ice would be a powerful, though currently unimaginable to measure, piece of evidence. Until a spacecraft can visit Varuna to perform this detailed forensic analysis, its origin will remain one of its most profound and captivating enigmas, a celestial cold case that stretches back to the very dawn of our Sun. The intricate gravitational dance of the solar system extends far beyond the neat circles of the planets, into the dark and seemingly chaotic realm of the Kuiper Belt. Here, amidst the icy wanderers, orbits are often not random, but are instead locked into subtle, long-distance relationships known as resonances. These are not physical collisions, but rhythmic gravitational harmonies where the orbital periods of two bodies form a precise ratio, like two pendulums swinging in sync across a vast room. Neptune, as the gravitational heavyweight of the outer system, acts as the primary conductor for this cosmic orchestra, shepherding countless objects into resonant patterns that provide long-term stability. The great mystery surrounding Varuna is whether it too is a participant in this silent ballet, or if its wild, eccentric path is a solo performance of pure chaos. Detecting a resonance for an object like Varuna is an astronomical challenge of the highest order. It requires tracking its position with exquisite precision over decades or even centuries to discern the faintest rhythmic pattern in its motion against the background of stars. A true mean motion resonance with Neptune would mean that for every certain number of orbits Varuna completes around the Sun, Neptune completes a different specific number. A common resonance in the Kuiper Belt is the 2 to 3, where an object orbits twice for every 3 of Neptune's trips around the Sun. The evidence for Varuna, however, is murky and hotly debated. Some dynamical models suggest its orbital parameters are close to, but not perfectly locked into, a resonant state. It might be what's known as a transient resonance, where it gets temporarily captured by Neptune's gravity for a period of time, only to be kicked out again by the subtle influences of other large Kuiper Belt objects or the lingering gravitational potential of the galactic tide. This ambiguity is profoundly important. If Varuna is definitively found to be in a stable resonance, it would be a powerful clue that its current orbit is not a product of a single, violent gravitational kick, but rather a carefully maintained path, a cosmic parking spot where Neptune's gravity protects it from close encounters and eventual ejection from the solar system. This would strongly support the planetary migration models, as these resonances are like fossilized records of Neptune's outward journey. The ice giant would have swept these resonances along with it, populating them with objects like Varuna as it moved. Its orbit would be a living snapshot of that ancient migratory event. Conversely, if Varuna is proven to be completely free of any resonant ties, it becomes an even greater enigma. Its stability over billions of years would then have to be explained by other, more exotic factors. Perhaps it is protected by the gravitational influence of the hypothetical planet 9, whose predicted presence in the extreme outer solar system could be shepherding a whole population of objects into similar, high-inclination, stable orbits without the need for a resonance with Neptune. Or maybe its orbital parameters are simply fortunate, placing it in a safe zone where the combined gravitational tugs of the known giant planets cancel each other out in a delicate balance, allowing it to persist in its chaotic path without being destroyed. The implications of solving this resonant riddle stretch far beyond cataloging Varuna's path. It serves as a critical test for our grand models of solar system evolution. The NICE model, for instance, which describes the violent reshuffling of the giant planets, makes specific predictions about how the Kuiper Belt should be populated, including the distribution of objects in various resonances. Where Varuna falls in this distribution firmly in a resonance, on the edge, or completely outside provides a crucial data point that either validates or forces a revision of these theories. It helps us understand the efficiency with which Neptune scattered objects during its migration and the subsequent gravitational calm that allowed the system to settle into its current configuration. Ultimately, the question of Varuna's orbital resonance is a testament to the interconnectedness of the solar system. It demonstrates that no world, no matter how distant and isolated it may appear, is an island entirely unto itself. Its motion is a product of a complex gravitational history written by the planets, a history we are still learning to read in the subtle rhythms of the dark. Yet for all the gravitational interplay with Neptune and the potential influence of unseen planets, Varuna appears to be profoundly, mysteriously alone. This brings us to our 12th great mystery, the confounding absence of any moons. In the expansive neighborhood of the Kuiper Belt, having a companion is practically the norm rather than the exception. A staggering number of objects out there, many of them significantly smaller than Varuna, are known to possess at least one satellite. The dwarf planets Pluto, Haumea, and Makemake all have families of moons. Even smaller bodies, like the 63-mile-wide asteroid Cleopatra, have been found with orbiting companions, for a world of Varuna's substantial size, estimated to be over 600 kilometers in diameter. The statistical probability of it having a moon is incredibly high. Yet, despite repeated and meticulous searches using the most powerful telescopes on Earth and in space, not a single definitive satellite has been found. This isn't just a minor curiosity, it's a glaring anomaly that sets Varuna apart from its peers and points to a uniquely violent or unstable history. One of the most compelling explanations for this loneliness points directly to Varuna's most defining characteristic, its incredibly rapid rotation. A world that completes a full turn on its axis every 6 hours and 20 minutes is spinning at a rate that creates a hostile environment for moon formation. The standard model for how moons are created involves a much more sedate process. Often, they form from a disk of debris left over after a giant impact, gently coalescing into a satellite over time. Other times, they are captured when a smaller object passes too close and is gravitationally snared. Varuna's frantic spin throws a wrench into both of these mechanisms. The tremendous centrifugal force generated at its equator would make it exceedingly difficult for any loose material to accrete into a moon. It would simply be flung away. Furthermore, the region of gravitational dominance around a rapidly spinning body, known as its Hill sphere, can become distorted and unstable. For a potential moon to have a stable, long-term orbit, it would need to be located quite far from Varuna, making it exceptionally faint and difficult for our telescopes to detect against the blackness of space. This leads to the possibility that Varuna did have moons in the distant past, but they were tragically lost. The early Kuiper Belt was a far more crowded and violent place than it is today, a shooting gallery of primordial bodies crashing into one another. A single, catastrophic collision with another large object could have obliterated a nascent satellite system, shattering the moons into a fine dust that either escaped into space or settled back onto Varuna's surface. Alternatively, the gravitational influence of the giant planets, particularly Neptune, might have played the role of a cosmic thief. If a moon's orbit was perturbed just right during a close pass billions of years ago, Neptune's immense gravity could have plucked it away, stealing Varuna's companion, and either ejecting it from the solar system entirely or capturing it as a new moon of its own. This would be a one-time event, leaving Varuna permanently orphaned. There is also a more subtle, dynamic reason for the absence: orbital decay driven by tidal forces. If a moon did form and managed to achieve a stable orbit, the gravitational interplay between it and Varuna would have created tidal bulges on both bodies. Over millions of years, the energy exchanged through this process can cause a moon's orbit to gradually decay. For a moon that formed too close to its parent body, this could eventually lead to a dramatic demise, with the satellite crossing the Roche limit, the point where gravitational tidal forces exceed the moon's own structural integrity, and being torn apart into a temporary ring system before the debris finally rains down onto the surface. We see evidence of this process happening today with Mars's moon Phobos, which is slowly spiraling inward. Varuna may have simply consumed its own children long ago. Of course, we must also confront the very real and practical possibility that our technology has not yet caught up to the challenge. Detecting a moon around an object as distant and faint as Varuna is a monumental task. It would require not only immense light-gathering power, but also supremely sharp resolution to distinguish a faint pinprick of light located incredibly close to its parent world. Any moon would likely share the same dark, low-albedo surface as Varuna itself, making it absorb most of the feeble sunlight that hits it and reflecting very little back toward our telescopes. Current observations have placed stringent limits on what could be there. We can say with confidence that there is no large, Charon-sized moon orbiting Varuna. But a smaller moon, perhaps only a few dozen kilometers across, or one orbiting very close to the dark surface, could easily be hiding in the glare or lost in the noise of our observations. The advent of next-generation instruments like the James Webb Space Telescope and the upcoming extremely large telescopes on the ground, with their unprecedented sensitivity and resolution, might finally unveil a tiny, hidden companion, solving this mystery by revealing that Varuna was never truly alone after all. Until then, its solitary dance through the darkness remains one of its most enduring and puzzling features. While the profound darkness of its surface presents one visual mystery, the specific hue of that darkness offers another tantalizing clue. When astronomers analyze the sunlight reflecting off Varuna, they don't just see a generic gray, they detect a distinct and pervasive reddish tint. This isn't the brilliant crimson of Martian rust, but a subtler, deeper shade, like ancient brick or dried blood, that sets it apart from the more neutral grays of many other denizens of the Kuiper Belt. This coloration is a direct signature of complex chemistry occurring in the deep freeze of space, a process that transforms simple ices into the ruddy, complex organic compounds that may hold the building blocks of life itself. The prime suspect for this reddish palette is a class of substances known as tholins. This isn't a single chemical but a catch-all term for a wide variety of complex organic polymers that form when simple, carbon-containing ices like methane are bombarded by high-energy radiation. Imagine the surface of Varuna as a vast, open-air laboratory that has been running a single experiment for billions of years. The main ingredient is frozen methane scattered across the landscape. The energy source is the constant, relentless hail of cosmic rays from deep space and ultraviolet photons from the distant sun. This radiation acts like a microscopic hammer, slamming into the methane molecules and breaking them apart. The resulting fragments, carbon and hydrogen atoms, are highly reactive. They don't just sit there, they immediately begin recombining with each other and with any other available atoms, forging new, more complex molecules in a process known as radiolysis. Over eons, this relentless cosmic chemistry builds up long chains of carbon atoms, often incorporating nitrogen and oxygen, that link together into a sticky, tar-like substance. These tholins are notoriously dark and red, perfectly matching the spectral signature we see from Varuna. They are essentially the same kind of complex organic gunk that gives other distant worlds their distinctive colors, from the rusty plains of Pluto to the two-toned face of Saturn's moon Iapetus. The process is so efficient that it can effectively paint an entire world, creating a global layer of reddish sludge that could be meters or even tens of meters thick. The specific shade of red can even tell us about the age and composition of this layer. Newer tholins might be darker and redder, while older deposits, exposed to radiation for even longer, could eventually be processed into a darker, more neutral black. However, the story might not be so simple. While tholins are the leading explanation, other factors could be contributing to or even causing the reddish hue. The surface could be enriched with unusual mineralogical components that are intrinsically red. For instance, if Varuna's rocky core contains certain types of iron-rich silicates or complex oxides, and that material was brought to the surface through ancient cryovolcanism or a giant impact, it could impart a reddish color directly. We see this on Earth with minerals like hematite or cinnabar, and similar processes could be at work in the outer solar system. Alternatively, the presence of other ices could modify the color. Frozen ethane, a common product of methane irradiation, has a slightly yellowish hue that could mix with other compounds to create a reddish appearance. Even the physical texture of the surface plays a role. A very fine, powdery regolith can scatter light differently than solid ice, enhancing certain wavelengths and contributing to the overall color we perceive from Earth. The most dynamic possibility involves surface processes that have selectively altered this coloration over time. Varuna is not a static statue. Its eccentric orbit and potential internal heat drive change. Imagine a cycle where a fresh, bright layer of water ice is exposed by a landslide or cryovolcanic flow. This new surface would initially be nearly white. But as it is immediately exposed to the harsh radiation environment, it begins to darken and redden. The most volatile ices on this fresh surface, like nitrogen or carbon monoxide, would sublimate away quickly, leaving behind a lag deposit of darker, more resilient tholins and complex organics. This would create a feedback loop where the surface is constantly being renewed and then selectively darkened, with the reddest, most processed material always ending up on top. This could explain why the redness appears so uniform. It's the final, stable product of billions of years of space weathering. Understanding Varuna's color is far more than an exercise in interplanetary interior decorating. It provides a direct window into the chemical inventory of the primordial solar system and the processes that create complex organic molecules, the very precursors to life, in the most unlikely of places. This reddish hue is a badge that speaks of great age, of relentless bombardment, and of a complex geological history where chemistry and dynamics intertwine on a world-sized scale. It marks Varuna not as a barren ball of ice, but as a world that has been actively, chemically evolving in the darkness for eons. Yet for all the mysteries of its surface and composition, one of the most fundamental and surprisingly contentious questions about Varuna remains unanswered. Just how big is it? This isn't a matter of simple measurement error. It is a full-blown controversy in the astronomical community, with estimates for its diameter swinging wildly from a modest 500 kilometers all the way up to a staggering 1,000. This isn't just a debate over a number. This discrepancy strikes at the very heart of our understanding of this world's physical nature, its place in the solar system's hierarchy, and even the reliability of the tools we use to explore the cosmic dark. The root of this profound uncertainty lies in the immense challenge of measuring a faint, distant, and dark object. Unlike the planets, which we can visit with spacecraft to take direct measurements, determining the size of a Kuiper Belt object like Varuna is an exercise in indirect inference, a celestial detective story where each line of evidence comes with its own set of complications and potential for misinterpretation. Astronomers primarily rely on three distinct techniques, and each one tells a slightly different story. The first method involves direct imaging and measuring the object's apparent brightness or its visual magnitude. In a perfect world, if we know how reflective an object's surface is its albedo, and we know how bright it appears from Earth, we can easily calculate its size. A large, dark object can appear just as bright as a small, shiny one. This is precisely where the problem begins with Varuna. Its surface is among the darkest known, but we don't know exactly how dark. Early albedo estimates were highly uncertain, leading to those initial, wildly varying size guesses that spanned hundreds of kilometers. Refining this method requires a separate, independent measurement of either the size or the albedo to break the degeneracy, which leads us to the other techniques. The second approach, and often considered more reliable, is through thermal radiometry. This involves observing Varuna not in visible light, but in the infrared part of the spectrum where it emits heat. The amount of thermal radiation an object gives off is directly related to its size and its temperature. By modeling how it absorbs sunlight and re-radiates that energy as heat, astronomers can estimate its diameter. However, this method is also fraught with assumptions. The model requires an accurate understanding of the object's thermal properties. Is its surface smooth or rocky? Is it a good conductor of heat or a poor one? Most critically, Varuna's rapid rotation and highly elongated shape throw a massive wrench into these models. A spherical model will give one answer, while an ellipsoidal model, which we strongly suspect is the correct shape, will give a completely different result because it presents a changing surface area to the Sun and to our telescopes. A failure to properly account for this bizarre morphology can lead to size estimates that are significantly off. The third and most definitive method is the stellar occultation. This is when Varuna passes directly in front of a distant star, acting like a natural celestial micrometer. By carefully timing the duration of the stars dimming from multiple observing locations on Earth, astronomers can trace out the precise profile of the object's shadow and thus measure its dimensions with incredible accuracy. Occultations have been the gold standard for sizing up distant solar system bodies, but they are incredibly difficult to catch. They require precise predictions of Varuna's path and a coordinated effort by telescopes scattered across the globe. The few successful occultations of Varuna have provided crucial data, but they have also added to the puzzle. They confirmed its elongated shape but have still yielded slightly differing size estimates, partly because the orientation of the object during each event can change the observed cross-section. This ongoing controversy over a single number has cascading consequences for nearly every other aspect of our understanding. The size is the key that unlocks Varuna's density, which, as we discussed, is itself a profound mystery. A larger diameter combined with a given mass estimate results in a much lower density, supporting the rubble pile model. A smaller diameter with the same mass points to a much denser, more rocky and differentiated world. Its classification status also hangs in the balance, the unofficial threshold for a dwarf planet. An object massive enough to be rounded by its own gravity is generally thought to be around 800 kilometers in diameter. If Varuna is on the higher end of the size estimates, it would be a clear candidate for dwarf planet status. If it is on the lower end, its extremely elongated shape might indicate it lacks the gravitational dominance to achieve hydrostatic equilibrium, relegating it to the category of a large but irregular trans-Neptunian object. Ultimately, the size discrepancy is a powerful, humbling reminder. It shows that even in an age of advanced telescopes and space probes, some of the most basic facts about our own solar system's inhabitants remain just out of reach, waiting for better technology, a fortunate occultation, or perhaps a dedicated mission to finally settle the argument and give this enigmatic world its true measure. But the very concept of seasons on a world so far from the sun seems almost paradoxical. How can a place where the sun is little more than the brightest star in a perpetual black sky experience any meaningful seasonal change? The answer lies not in axial tilt, but in the incredible stretch of its elliptical path. Varuna's journey is a cosmic pendulum swing of temperature, a cycle of profound climatic shifts driven entirely by its changing distance from our star. At its closest approach, perihelion, it ventures to a mere 40 astronomical units from the sun. While still desperately cold by any earthly standard, this proximity provides a significant boost in solar energy compared to its farthest point. When it reaches aphelion, over 100 astronomical units out, the sunlight it receives is less than a quarter of what it gets at perihelion. This isn't a subtle difference, it's a dramatic four-fold variation in solar heating that unfolds over a cycle lasting 140 Earth years. This creates a seasonal rhythm unlike any other, where a single summer or winter lasts for decades, a slow-motion dance of freeze and thaw across a landscape of ice and rock. These extreme temperature swings are not just abstract numbers, they have the power to fundamentally alter the state of matter on Varuna's surface. The most volatile ices in its chemical inventory, namely nitrogen, carbon monoxide, and even methane, have sublimation points that sit tantalizingly close to the estimated temperature range Varuna experiences. During its long, multi-decade summer near perihelion, the slight increase in warmth could be just enough to trigger the sublimation of these surface ices. Picture a world where vast, frozen plains of nitrogen begin to stir, their outermost molecules gaining just enough energy to break free and jump directly from a solid into a gas. This process would not create rivers or lakes, but it could potentially generate a transient, ultra-thin atmosphere, a temporary shroud of gas that hugs the surface for a few precious decades before the deepening cold of aphelion forces it to freeze out once again, snowing back down as a fresh layer of frost. This cycle of atmospheric breath and retreat could be the primary driver of geological change, a slow exhale and inhale that reshapes the world over centuries. The potential for this seasonal activity raises the thrilling possibility of observable change. If we could monitor Varuna closely over a period of decades, we might be fortunate enough to witness its surface transform in real time. As it approaches and passes perihelion, the slight warming could cause the most volatile ices to sublimate from areas exposed to direct sunlight, perhaps retreating from darker, warmer regions and depositing as bright frost in colder, permanently shadowed craters. This would create a shifting pattern of light and dark across its surface, directly affecting its overall reflectivity and potentially explaining some of the irregular variations in its light curve that have so puzzled astronomers. We might be seeing not a static world, but a snapshot of a specific season in its immensely long year. A fresh, bright frost deposit could make it appear suddenly brighter for a time, while a period of sublimation and dark lag deposit formation could cause it to dim. Its surface could be a dynamic canvas where the sun, despite its weakness, is still an active artist. The effects likely reach beneath the surface as well. This cyclical heating and cooling would create thermal stresses within the upper layers of the crust. As the surface expands and contracts over these long seasons, it could generate powerful forces, leading to the formation of new fractures and faults. This thermal tectonics could be the engine that drives cryovolcanism, reopening old vents and creating new pathways for any warm, slushy material from the interior to reach the surface. Each perihelion passage could therefore be a period of renewed geological activity, a time when Varuna is most alive, with its internal heat finding new ways to express itself through cracks in the icy shell opened by the sun's gentle, periodic push. The seasons on Varuna are not about leaves changing color or snow falling. They are about the very architecture of the world slowly flexing and responding to a rhythmic pulse of energy that has continued unabated for billions of years. All these clues, the frantic spin, the distorted shape, the profound darkness of its surface, converge on a single, violent explanation, a cataclysmic impact in the deep past. This isn't merely a theory, it's a forensic reconstruction of the most dramatic day in Varuna's long history, an event that likely shaped its very essence. The numbers tell a story of incredible violence. To accelerate an object of Varuna's estimated mass to its current dizzying rotation rate would require a transfer of energy so immense it defies easy comprehension. The most plausible culprit is a grazing collision with another substantial body, perhaps hundreds of kilometers across, striking a primordial, slower spinning Varuna not with a direct, shattering blow, but with a side-swiping impact that acted like a colossal cosmic cue ball, setting it spinning for eons. The physics of such an event are both brutal and precise. The angle of impact would have been everything. A head-on collision would likely have shattered both bodies into a cloud of debris, some of which might have recoalesced into a completely new object. A perfectly tangential strike, however, would impart the maximum rotational energy. Scientists modeling these scenarios suggest the impactor would have needed to be roughly 1/3 to half of Varuna's own size, traveling at a relative velocity typical of the early Kuiper Belt, a sedate pace of perhaps just 1 or 2 kilometers per second. While that sounds slow compared to the velocities of inner solar system impacts, at that speed a rock the size of a small country carries apocalyptic force. This wasn't a high-speed crash, it was a slow-motion tectonic merger, a gravitational dance that ended in a decisive, shape-altering embrace. The prevalence of such giant impacts is a critical piece of the puzzle. Was Varuna uniquely unlucky, or was this a common rite of passage for large Kuiper Belt objects? The evidence points strongly toward the latter. We see the fingerprints of colossal collisions throughout the outer solar system. Pluto's giant moon Charon is believed to have formed from the debris of a giant impact. Haumea's incredibly rapid rotation, elongated shape, an entire family of orbiting fragments are a textbook example of a catastrophic collision. Uranus orbits the Sun tipped entirely on its side, almost certainly the result of a planet-shattering impact in its youth. This suggests the early Kuiper Belt was not a serene, orderly place, but a chaotic shooting gallery where such violent encounters were a fundamental part of the growth and evolution of planetary bodies. Varuna's spin is not an anomaly, it is a standard scar from a more violent time, a fossilized record of the chaos that reigned during the final stages of planetary accretion. The aftermath of such an impact would have been as transformative as the event itself. The tremendous energy delivered would have generated enough heat to partially melt Varuna's interior, potentially triggering the differentiation that might explain its higher density estimates. This internal melting would have caused heavier rocky material to sink toward the center, forming a core, while lighter ices rose to form a mantle and crust. Simultaneously, the impact could have stripped away any primordial atmosphere Varuna might have possessed and blasted much of its original, brighter surface ice into space, leaving behind a shattered, darkening landscape. The impact might have even generated a temporary ring system or a family of moonlets which could have either escaped, fallen back to the surface, or been lost to gravitational perturbations over billions of years, explaining its current solitary existence. This single event could therefore be the master key that unlocks multiple mysteries. It explains the rotation, suggests a cause for differentiation, accounts for the dark surface, and provides a reason for the lack of moon. In many ways, the Varuna we infer today is a product of that one ancient, world-altering collision, a phoenix born from a fire of ice and rock in the darkness of the young solar system. But the mystery of what coats Varuna's surface runs even deeper than its overall color or darkness. When astronomers break down its reflected light into a detailed spectrum, a chemical fingerprint that reveals the specific molecules present, they encounter features that defy easy explanation. Certain absorption bands, the telltale dips in the spectrum where light is absorbed by particular chemicals, don't align perfectly with the signatures of any known ices or minerals we've catalogued from other worlds. It's as if we're reading a familiar language but discovering entirely new words, suggesting that Varuna's surface chemistry might be brewing compounds under conditions so unique that we haven't yet replicated or identified them in our laboratories. One compelling possibility is that we are witnessing the creation of novel types of tholins or other complex organics. The process of radiolysis, driven by relentless cosmic radiation, doesn't produce a single, simple substance. It generates a vast and messy family of polymers, and the exact mixture depends heavily on the local conditions. The temperature, the specific blend of starting ices, the intensity and type of radiation, and the timescale over which the reaction has been running. Varuna's particular orbital history, with its extreme temperature swings and potential internal heat, may have created a perfect laboratory for synthesizing a unique cocktail of organic gunk. The subtle shifts in its spectral bands could be the signature of these exotic new compounds, perhaps with longer carbon chains or different molecular structures than those found on Pluto or Triton. This wouldn't just be a curiosity, it would provide a crucial window into the probiotic chemistry that can occur in the freezing outer solar system, showing us a wider range of organic complexity than we ever imagined. However, we must also confront the tantalizing and humbling possibility that these unexplained features are not chemical at all, but physical. Varuna's incredibly rapid rotation presents a monumental challenge for taking a clean spectral reading. From our distant vantage point, we are never looking at a single, static hemisphere for long. Instead, we are capturing a constantly shifting, blurred average of its entire surface as it tumbles through its 6.3-hour day. If Varuna's terrain is as dramatically heterogeneous as we suspect, with vast plains of dark tholins right next to sheer cliffs of pure water ice, then the spectrum we measure will be a messy composite. An absorption feature that appears weak and broad in our data might not be from a new compound, but could simply be the result of a sharp, strong feature from a small, highly reflective icy region being diluted and smoothed out by the overwhelming darkness of the surrounding terrain. We are, in effect, trying to discern the ingredients of a stew by only being allowed to taste the entire pot with one spoonful, unable to isolate the individual flavors. This blurring effect is compounded by Varuna's highly elongated shape. As it spins, the cross-sectional area it presents to our telescopes changes dramatically. This means the relative contribution of different surface materials to the total spectrum is in constant flux. A specific unexplained dip in the data might appear and disappear not because of a change on Varuna itself, but simply because a particular terrain type has rotated into or out of view. Disentangling this rotational smearing from genuine chemical signatures is one of the biggest challenges in modern planetary astronomy, requiring sophisticated computer models that account for the object's shape, spin state, and hypothesized surface map. Until we can observe Varuna with a resolution that allows us to see its individual features, these unexplained spectral bands will remain a tantalizing puzzle, a siren's call that could either lead us to a breakthrough in cosmic chemistry or simply reveal the limits of our current observational methods. But the story of how Varuna came to be in its current, looping path is one of the grandest puzzles of all. Its wild, eccentric orbit is a profound anomaly, a path so stretched and inclined that it simply doesn't fit the profile of a serene local formation. This isn't the gentle circle of a world that condensed peacefully from the solar nebula right where it sits. This is the trajectory of an object that has been gravitationally manhandled, a cosmic billiard ball that was decisively struck and sent careening across the outer solar system. To understand its journey is to open a window into the most dynamic and violent chapter of our solar system's history, a time when the giant planets themselves were on the move, reshaping the entire architecture of our planetary neighborhood. The most compelling narrative for Varuna's migration begins not in the cold darkness of the Kuiper Belt, but in a region much closer to the warmth of the young sun. Billions of years ago, during the final stages of planetary accretion, the orbits of the giant planets were not the stable, well-spaced circles we see today. Models like the NICE model suggest that Neptune, Uranus, and Saturn underwent a profound outward migration, shifting their positions dramatically as they interacted with a vast disk of leftover planetesimals. As Neptune moved outward, its immense gravitational influence acted like a celestial plow, scattering countless icy bodies before it. Some were flung inward to become the Jupiter family comets that occasionally visit our inner solar system. Others, like Varuna, were given a powerful gravitational kick that ejected them outward onto stable but highly eccentric and inclined orbits in what we now call the Kuiper Belt. In this story, Varuna is not a native of its current home, but an immigrant pushed out to the frontier by the expansion of the solar system's great powers. Its orbit is not an original feature but a badge of honor, a permanent record of a close encounter with a giant that occurred over 4 billion years ago. This scattering theory is powerfully supported by the very nature of the Kuiper Belt's population. Astronomers divide these distant objects into two broad categories: the cold classical population, which orbits in neat, circular, low-inclination paths, and the hot population, to which Varuna belongs, characterized by these wild, eccentric, and highly inclined orbits. The cold population are thought to be the true locals, having formed more or less in place and remaining relatively undisturbed. The hot population, however, are the textbook example of gravitational scattering. Their orbits are exactly what sophisticated computer simulations predict when you model the effects of Neptune's grand migration. Varuna, with its dramatic orbital stretch, is a classic member of this scattered hot population, its path a perfect fit for this ancient narrative of planetary upheaval. Yet, there are dissenting voices and alternative timelines. Some dynamical models propose that while the scattering event is real, it may have happened much more recently than the initial planetary migration. The early Kuiper Belt was a crowded and chaotic place, and gravitational interactions between large objects themselves could have provided the necessary push. Varuna might have had a close encounter with another large Plutino or Haumea-sized body, an event that perturbed its orbit into its current configuration long after Neptune had settled into its final position. This would make its dramatic path a more recent scar, a reminder that gravitational chaos did not end with the age of the giants, but has continued to subtly shape the outer solar system for eons. The most tantalizing clues to its origin, however, may be written not in its motion but in its composition. If Varuna did form much closer to the Sun, say between the orbits of Saturn and Uranus, it would have condensed in a significantly warmer environment than the classical Kuiper Belt. This warmer birthplace would have left a subtle but detectable imprint on its chemical inventory. We might expect a lower abundance of the most super-volatile ices like nitrogen and carbon monoxide, which struggle to condense at higher temperatures. Its water ice might show a different isotopic ratio, or its complement of organic molecules might be more complex, having been baked for longer in the slightly warmer protoplanetary disk. Unfortunately, measuring these details from across billions of miles of space is currently beyond our reach, a tantalizing set of questions that only a dedicated spacecraft mission could answer. For now, the migration mystery remains a captivating blend of orbital dynamics and forensic chemistry, a celestial cold case where the clues are written in gravity and ice, waiting for us to become clever enough detectives to finally piece together the full story of Varuna's incredible journey. But to truly understand Varuna, we can't view it in isolation. We must see it as part of a much larger family portrait. The region beyond Neptune is not a random scattering of icy debris, but a carefully organized, albeit chaotic, archive of solar system history, with objects sorted into distinct dynamical families based on their orbits. Varuna's relationship to these groups is our 19th great mystery, a puzzle that asks whether this world is a typical member of a known clan or a unique outlier that defies all categorization, and what its position in this celestial census can tell us about its own origins and the evolution of the entire outer solar system. The most immediate family we can place Varuna in is the broad class of hot classical Kuiper Belt objects. This is a crucial distinction. The Kuiper Belt is divided into two major populations, the cold classics and the hot classics. The cold population orbits in relatively circular, low-inclination paths, suggesting they have resided in the Kuiper Belt since formation, relatively undisturbed and pristine. The hot population, which includes Varuna, is entirely different. These objects have highly eccentric and inclined orbits, just like Varuna's dramatic, stretched path. They are the scattered survivors, the ones that were gravitationally stirred up and excited, most likely by Neptune's outward migration during the solar system's youth. By being a member of this hot population, Varuna immediately tells us a story of displacement and violence. It was not formed peacefully in place. Its very orbit is a scar from an ancient gravitational encounter, a permanent record of the chaos that reigned as the giant planets settled into their current positions. Yet, when we look closer, Varuna doesn't fit perfectly into any of the more specific, tightly bound families within the Kuiper Belt. It is not, for instance, a Plutino. Plutinos are a fascinating group of objects locked in a precise 2 to 3 orbital resonance with Neptune, meaning they complete 2 orbits for every 3 of the ice giant's trips around the Sun. This resonance protects them and defines their paths. Varuna's orbit does not place it in this resonant club. Similarly, it is not a member of the scattered disk in the purest sense, a population of objects with extremely eccentric orbits that take them hundreds of astronomical units from the Sun, often with perihelia very close to Neptune. Varuna's orbit is eccentric, but not quite to that extreme degree, placing it in a kind of transitional zone between the classical Kuiper Belt and the scattered disk. This lack of a neat label makes it a fascinating transitional object, a world that embodies characteristics of different populations, perhaps because it was one of the last bodies to be scattered during Neptune's migration, receiving a gravitational kick that was strong enough to excite its orbit but not quite powerful enough to fling it into the deepest reaches of the scattered disk. This ambiguous classification extends to its physical characteristics as well. When we compare Varuna to other large trans-Neptunian objects, its uniqueness becomes even more apparent. Take, for example, the dwarf planet Makemake. Both are similar in size, both reside in the Kuiper Belt, and both have surfaces rich in methane. Yet, Makemake is known to have a tenuous atmosphere, while Varuna's sky appears utterly empty. Why the difference? It could be a matter of temperature, with Makemake's slightly more distant and stable orbit providing colder conditions that help retain surface ices. Or it could point to a fundamental difference in internal heat and geological activity. Then there's Haumea, another rapidly rotating, elongated world. While both share the trait of a distorted shape spun up by a giant impact, Haumea is surrounded by a family of smaller objects and has 2 moons, a testament to its violent past. Varuna, by contrast, orbits in profound solitude, its own impact history seemingly leaving no such permanent entourage. These comparisons are not just a list of facts, they are a forensic toolkit. By understanding what makes Varuna different from Makemake and Haumea, we isolate the specific variables like the angle and energy of its formative impact or the precise mix of its internal ices. that determine the ultimate fate of these distant worlds. Perhaps the most compelling way to view Varuna is not as a member of a specific family, but as a vital link in a continuum of evolution. Its properties place it squarely between the smaller, primitive, unevolved comet-like bodies of the Kuiper Belt and the larger, fully differentiated, geologically complex dwarf planets like Pluto and Eris. It possesses a mix of primordial and evolved characteristics that make it a perfect transitional specimen. Its dark, red surface coated in complex organics speaks of great age and primitive chemical processing, a hallmark of the smallest KBOs. Yet its rapid rotation, elongated shape, and potential for past internal heating and differentiation are traits we associate with the largest and most planet-like bodies. Varuna may represent a critical size threshold, a window into the processes that begin to occur when an icy body grows large enough for gravity and collisions to start transforming it from a simple aggregate of ice and rock into a more complex, layered world. Studying where it fits and where it doesn't helps us draw the family tree for everything that orbits in the cold, dark vastness beyond Neptune, revealing the evolutionary pathways that turn simple ice balls into complex worlds. Peering past the cracked and frozen surface of this distant world, we arrive at a mystery that lies at the very heart of Varuna, the enigmatic puzzle of its internal structure. Is it a simple, homogeneous ball of mixed rock and ice, a primordial relic frozen in time since the birth of the solar system? Or has it undergone a profound planetary metamorphosis, differentiating into distinct layers of a dense rocky core surrounded by a mantle of ice, and perhaps even cradling a hidden, liquid ocean in its depths? The answer to this question would fundamentally redefine Varuna from a simple cosmic fossil into a complex, evolving world, and it's a question that hinges on a delicate balance of heat, chemistry, and the relentless force of its own spin. The possibility of differentiation is perhaps the most transformative idea. For a world to separate into a core and mantle, it must have been warm enough in its past to literally melt from the inside out. In the early solar system, the most likely source of this internal furnace was the decay of short-lived radioactive isotopes, particularly aluminum-26. This potent heat source has a half-life of only 700,000 years, a mere blink in cosmic time, but it burns hot and fast. If Varuna formed quickly enough, within the first few million years of the solar system's existence, it could have incorporated enough of this radioactive material to trigger a significant meltdown. In this molten state, physics takes over. The heavier, denser rocky material slowly sinks inward, pulled by gravity, while the lighter ices like water, methane, and ammonia rise to the surface, forming a layered structure. This isn't just theoretical. We see evidence of this process in asteroids like Vesta, and it's the foundational event that creates geologically active planets. If Varuna is differentiated, it suggests a far more dynamic and complex history than its frozen exterior implies. But what if that internal heat didn't just vanish billions of years ago? This leads us to the most thrilling possibility, a subsurface ocean. The concept of liquid water existing on a world so distant from the sun seems at first like a contradiction. Yet we now know that such hidden seas are not only possible but might be common in the outer solar system, thanks to a clever combination of heat and antifreeze. Even the feeble warmth from the long-term decay of radioactive elements like potassium, uranium, and thorium could provide a baseline of heat. More importantly, Varuna's interior is likely rich in ammonia. When mixed with water, ammonia acts as a potent antifreeze, dramatically lowering the freezing point of the mixture. A sludge of water ammonia could remain liquid at temperatures as low as -100 degrees Celsius, conditions that are easily achievable deep within Varuna's icy shell. This wouldn't be a vast, globe-spanning ocean like on Europa, but perhaps a regional layer of thick, briny water sandwiched between the rocky core and the solid, icy mantle above, a dark, pressurized aquifer that has been completely isolated from the universe for billions of years. The wild card in all of this is Varuna's incredibly rapid rotation. This isn't a minor detail, it's a fundamental force that constantly churns and stresses its interior. Think of it like spinning a raw egg versus a hard-boiled one. The liquid inside the raw egg reacts to the spin, creating internal currents and pressures. For Varuna, this relentless tumbling could generate significant internal friction within its malleable, potentially porous structure. This frictional heating, however slight, could provide a crucial extra source of energy, helping to maintain a subsurface ocean long after its radioactive heat has begun to wane. Furthermore, this spin places the entire world under immense centrifugal force, which could dramatically affect the shape and dynamics of any internal liquid layer. The ocean itself might be thicker at the equator and thinner at the poles, and the currents within it would be shaped by the Coriolis effect, just like hurricanes on Earth, creating a unique and complex hydrosphere utterly unlike any other. This internal activity would not be contained, it must express itself on the surface. The potential for cryovolcanism becomes a direct consequence of a warm, layered interior. If a subsurface ocean exists, the heat from below and the constant flexing from the spin would seek outlets. This pressure could force slushy, ammonia-rich water up through fractures in the brittle outer ice crust, erupting onto the surface in a slow-motion geyser of icy slurry. These cryovolcanic flows would instantly freeze in the vacuum of space, creating bright, fresh patches of crystalline ice on an otherwise dark landscape. This process offers an elegant solution to multiple mysteries. It could explain the puzzling bright spots in its light curve, the potential resurfacing that keeps its water ice in a crystalline state, and the replenishment of volatile ices that might otherwise sublimate away. The rapid rotation also influences this geology, as the constant stress could constantly open new fractures and vents, making Varuna a more dynamically active world than its frozen, distant location would ever suggest. Ultimately, the puzzle of its interior is the master key that unlocks every other secret. It is the hidden engine that dictates the geology, chemistry, and very life story of this mesmerizing world on the edge of darkness. These subtle asymmetries in the light curve are far more than just noise. They are a high-resolution readout of the world's topography and composition, a complex signal we are only just beginning to decode. Unlike a perfect ellipsoid, which would produce a smooth, symmetrical pattern of brightening and dimming as it rotates, Varuna's light curve shows small but significant kinks and offsets. The peaks and troughs of its brightness don't align perfectly with the predicted timing based on its 6.3-hour rotation. The rise to maximum brightness might be slightly steeper than the fall, or a minor dip might appear on one side of the light curve but not the other. These irregularities are the whispers of real, physical features on its surface, the first hints of its actual geography emerging from the blur of distance. One of the most compelling explanations for these asymmetries is the presence of a colossal impact basin, a scar from an ancient collision so vast it fundamentally warps the pattern of light and shadow. Imagine a single crater hundreds of kilometers across, gouged into Varuna's icy surface. As this gigantic depression rotates into view, its deep interior would be cast in profound shadow, creating a sharp, sudden drop in the overall brightness that wouldn't occur on a perfectly smooth world. Then, as the crater rotates toward the limb, its far rim might catch the faint sunlight at just the right angle to create a brilliant, glinting peak of brightness before the world dims again. This combination of a deep shadow and a bright rim would create a distinctly asymmetrical signature in the light curve, a fingerprint of a specific, gigantic feature that permanently alters the rhythm of its light. Alternatively, the answer may lie not in topography but in stark chemical contrasts. Varuna's surface is likely a patchwork quilt of different materials. Vast plains of pitch-black, radiation-processed tholins could lie adjacent to smaller, brilliant exposures of pristine water ice. As this mottled surface rotates, the transition from a very dark region to a very bright one would be abrupt, causing a sharp rise in the light curve. The transition from bright back to dark, however, might be more gradual if the boundary between the two terrains is less distinct. This would create the observed asymmetry in the slope of the light curve's peaks and valleys. We are essentially watching the changing reflectivity of a tumbling world, and the irregularities tell us that its surface is not uniformly processed by space weather, but is instead a complex record of geological renewal and ancient decay happening side by side. The most dynamic possibility involves real-time change. Varuna's extreme elliptical orbit subjects it to dramatic temperature swings. When it is near perihelion, the slight increase in solar energy could be just enough to trigger the sublimation of the most volatile ices on its sun-facing side. Picture a patch of nitrogen frost, highly reflective, slowly vanishing directly into gas, revealing the darker material underneath. This process would cause a gradual, asymmetric dimming on one part of the world that isn't mirrored on the other. Conversely, as it moves away from the sun, those volatiles could recondense as frost in permanently shadowed craters, creating a new, temporary bright spot that alters the light curve in a way that doesn't repeat with each rotation, but instead evolves over months and years. We may be witnessing the slow, seasonal breathing of a volatile cycle on a world where a single season lasts for decades, a process that paints and repaints the surface in ways that subtly disrupt the simple rhythm of its spin. Now we arrive at a process so slow and subtle it's almost imperceptible, yet over billions of years it has the power to fundamentally rewrite the chemical signature of an entire world. The relentless weathering of Varuna's surface by cosmic rays. Imagine a constant, invisible hail of high-energy particles, protons, and atomic nuclei accelerated to nearly the speed of light, screaming across interstellar space from distant supernova and other cataclysmic events. For over 4 billion years, this hail has been bombarding Varuna's frozen surface, and unlike the occasional dramatic impact of a large asteroid, this is a form of weathering that works with the patience of geology, a slow-motion sandblasting on an atomic scale that has likely transformed its entire outer layer. The primary victims of this onslaught are the simplest molecules in Varuna's icy crust: frozen methane, water, and nitrogen. When a cosmic ray packing immense energy slams into one of these molecules, it doesn't just give it a gentle nudge. It acts like a microscopic cannonball, shattering the molecular bonds and blasting the constituent atoms apart. This process, known as radiolysis, is the foundational force behind the creation of Varuna's complex chemistry. The shattered fragments, carbon, hydrogen, oxygen, and nitrogen atoms, are left in a hyper-reactive state. They don't remain free for long. They immediately begin ricocheting around and recombining with each other into new, more complex configurations. Over eons, this relentless cycle of destruction and recombination builds up long-chain carbon molecules, eventually forming the thick, sticky, tar-like substances we call tholins. These tholins are not a single compound but a vast family of complex organic polymers, and they are notoriously dark and red, perfectly matching the spectral signature we observe from Varuna. This isn't a quick process, it's a cosmic paint job applied one molecule at a time over the entire age of the solar system, and it is almost certainly the primary reason Varuna appears as a dark, ruddy spectre in our telescopes. But could this process alone account for the entirety of its surface properties? The answer is likely more nuanced. The efficiency of cosmic ray weathering depends heavily on two key factors: depth and time. The most energetic cosmic rays can penetrate several meters into solid ice, but their destructive power is greatest right at the surface. This suggests that Varuna's famous dark red layer is probably a relatively thin veneer, perhaps only a few meters thick, sitting atop a much larger body of more pristine, less processed ice. The constant churn of this process also creates a kind of equilibrium. As the topmost layer is irradiated into a thick crust of tholins, it actually begins to act as a protective shield for the ice beneath, absorbing the energy of incoming radiation and preventing it from penetrating deeper. This means the cosmic ray weathering is a self-limiting process. It creates its own ceiling. This might explain why Varuna isn't even darker. It reached a point where the buildup of dark gunk effectively slowed down the production of new gunk. This leads to a fascinating comparison with other denizens of the Kuiper Belt. Why does Varuna appear darker and redder than some of its neighbors? The answer may lie in their different orbital histories. An object with a more circular, stable orbit, like those in the cold classical population, would have experienced a relatively constant and predictable level of cosmic ray bombardment over its lifetime. Its surface processing would be uniform and steady. Varuna, with its wildly eccentric orbit, experiences dramatic swings in its local environment. When it soars out to aphelion, it spends centuries in the deepest freeze, where cosmic ray effects might proceed at a slightly different rate. When it plunges inward toward perihelion, the slight increase in solar wind pressure might actually push back against the flux of galactic cosmic rays, slightly moderating the weathering process for a time. This on-again, off-again cycle could have created a unique and complex layering in its tholin crust, different from the more uniformly processed surfaces of other objects. Furthermore, the presence of other ices can drastically alter the end product. If Varuna's surface has a significant amount of nitrogen ice mixed in with its methane, the cosmic ray chemistry will yield a different blend of organic compounds than if it were pure methane. Water ice is far more resistant to this kind of radiation darkening, which is why we see bright, reflective water ice features on other worlds despite their age. The specific cocktail of ices on Varuna's surface, therefore, acts as the recipe for its unique color and composition. We are essentially looking at the final product of a 4-billion-year-long chemical experiment, where the ingredients were Varuna's original ices and the laboratory equipment was the entire energetic force of the galaxy. This slow, relentless weathering hasn't just colored Varuna. It has fundamentally altered its very substance, creating a layer of complex organic molecules on its surface that are the precursors to the building blocks of life, a testament to the fact that even in the most frozen, distant, and seemingly lifeless reaches of our solar system, the universe is still quietly, patiently conducting chemistry. Yet to truly grasp the significance of Varuna, we must see it not merely as a solitary world, but as a unique and pristine time capsule, a relic that holds untarnished secrets about the very earliest conditions in our solar system. Every aspect of its being, from its peculiar mix of ices to its wild orbital path, acts as a forensic clue, allowing us to rewind the clock over 4.5 billion years and peer into the mysterious environment of the protoplanetary disk from which all planets were born. Unlike the rocky bodies of the inner solar system, which were baked by the sun and transformed by geology and impacts into entirely new forms, Varuna has resided in a permanent deep freeze. This profound and constant cold has acted as a perfect preservative, potentially locking within its structure a sample of the original building blocks of the solar system in a state of purity we simply cannot find anywhere else. The composition of its ices is perhaps the most direct window into this ancient past. When we detect methane and nitrogen frost on its surface, we are likely looking at materials that condensed directly from the solar nebula at staggering distances from the infant sun. The specific ratios of these ices and the isotopes they contain are a frozen record of the temperature and pressure conditions in its specific formation region. Think of the protoplanetary disk not as a uniform pancake of material, but as a vast temperature-graded kitchen. Closer to the stove, the sun, only the rockiest and most refractory materials could remain solid. But out where Varuna formed, in the deep freezer of the outer disk, even the most volatile and delicate compounds like nitrogen, carbon monoxide, and methane could freeze solid and be incorporated directly into growing planetesimals. By studying Varuna's composition, we are essentially reading the recipe book for that distant, cold region of the disk, understanding what raw ingredients were available to build the giant planets and their icy moons. This makes it a benchmark, a pristine sample against which we can compare the more processed and evolved compositions of objects that migrated or were heated, giving us a baseline for what the solar system looked like before gravity began its sculpting work. Furthermore, Varuna's very existence and substantial size challenge our models of how quickly planetesimals could form at such great distances from the Sun. The outer protoplanetary disk was far more diffuse than the inner regions. There was simply less material per unit of volume. For Varuna to have grown to over 600 kilometers in diameter out there suggests that the processes of accretion were incredibly efficient, or that the disk was more massive and rich in solids in its outer reaches than we previously believed. Its rapid rotation, likely imparted by a giant impact, provides even more crucial evidence. Such colossal collisions were only possible if the early Kuiper Belt was once a much more densely packed environment than it is today, a bustling construction zone where large bodies were common and interactions were frequent. Varuna is a silent witness to that era of chaotic growth and violent collisions. It's been a direct fossil of the dynamic and crowded conditions that existed before the giant planets cleared out and reshaped the entire region. Most critically, Varuna's dynamic history is a key piece of evidence in our understanding of planetary migration. Its current orbit, a classic member of the hot, scattered population of the Kuiper Belt, is a textbook signature of Neptune's outward journey. The NICE model, a leading theory of solar system evolution, predicts that as Neptune migrated outward, its gravity scattered a population of primordial objects into these very kinds of eccentric and inclined orbits. Varuna's path is not an oddity, it is a predicted outcome, a living validation of this grand model of planetary billiards. By studying its orbital parameters with ever-increasing precision, we can constrain the timing, speed, and extent of Neptune's migration, turning abstract mathematical models into a documented historical event. This transforms Varuna from a distant curiosity into a crucial anchor point in the timeline of our solar system's formation, a clock that started ticking during the solar system's most dynamic and transformative chapter. Ultimately, this world offers us a chance to study planetary building materials that have been kept in cold storage since the very beginning. The complex tholins on its surface, created by eons of radiation, are the kinds of complex organic compounds that were likely delivered to the early Earth by comets and asteroids. By studying them in their natural habitat on Varuna, we gain insight into the probiotic chemistry that may have seeded our own planet with the ingredients for life. In this way, Varuna is more than a fossil. It is a preserved piece of the solar system's original laboratory, a place where the experiments in chemistry and planet formation that began over 4 billion years ago are still yielding results today. Its value lies in its pristine nature, offering a glimpse of our own origins from the quiet, dark, and cold outer frontier where time itself seems to have stood still. But all these tantalizing mysteries, the rapid spin, the missing atmosphere, the unexplained density, are compounded by a far more practical and earth-bound challenge: the sheer, immense difficulty of actually observing Varuna from our planet. The quest to understand this distant world is a testament to human ingenuity, a constant battle against the fundamental limits of physics and technology, where every scrap of data is hard-won and shrouded in layers of uncertainty. The primary obstacle is, of course, distance. At an average of over 4 billion miles away, the sunlight that reaches Varuna is pathetically faint, and the minuscule fraction that makes the return journey to Earth is almost vanishingly small. To our most powerful telescopes, Varuna doesn't appear as a disk or even a discernible point of light. It is an ephemeral smudge, a whisper of photons against the profound blackness of space, requiring hours of painstaking exposure time just to confirm its existence. This incredible faintness is brutally compounded by the object's own profound darkness. A large, bright object at that distance would be challenging enough, but Varuna's surface, coated in that deep layer of light-absorbing tholins, reflects back a paltry 12 to 20% of the already feeble sunlight that touches it. This creates a perfect storm of observational hardship, a double whammy of distance and darkness that pushes our instruments to their absolute breaking point. Trying to determine its size becomes a maddening exercise in indirect inference, a celestial version of trying to judge the dimensions of a lump of charcoal from a mile away on a moonless night. Is it a large, dark world or a smaller, slightly less dark one? Without a definitive answer to this most basic question, every other calculation, its density, its mass, its internal structure, rests on a foundation of shifting sand. Then there is the complication of its frantic rotation. Most distant objects we study rotate sedately, allowing astronomers to build up a clear and stable light curve over many nights of observation. Varuna, spinning on its axis every 6 hours and 20 minutes, presents a moving target that changes its appearance dramatically in the time it takes to observe it. A single night of observation might capture 2 or 3 full rotations, each one presenting a slightly different cross-section and surface mix to our telescopes. This turns the process of photometry, precisely measuring its brightness, into a frantic attempt to assemble a coherent picture from a constantly shifting puzzle. The irregularities in its light curve, those tiny kinks and asymmetries that might hold the key to its topography, are easily lost in the noise of the atmosphere and the limitations of our detectors. We are trying to read the subtle nuances of a tumbling, distant world as if it were a book spinning in a hurricane. Our own atmosphere acts as a constant, blurring adversary in this endeavor. The turbulence of the air above our telescopes causes the light from distant stars to twinkle, a beautiful sight to the naked eye but a nightmare for astronomers seeking precision. This atmospheric seeing smears out the tiny point of light that is Varuna, preventing us from resolving any surface details and blending its signal with the background noise of the sky. While adaptive optics systems on giant telescopes like Keck or the VLT can correct for much of this distortion, they are fighting an uphill battle against such a faint and difficult target. Furthermore, Varuna's position in the sky limits which telescopes can observe it and for how long, adding another layer of logistical complexity to an already Herculean task. The limitations of our current technology therefore act as a veil, obscuring the true nature of Varuna and directly contributing to the enduring mysteries that surround it. The conflicting size and density estimates are a direct result of our inability to measure it directly. The question of a transient atmosphere remains open because our spectrographs lack the sensitivity to detect the ultra-thin spectral signatures of gases like nitrogen or methane from across the solar system. The potential for cryovolcanic activity or other surface changes remains speculative because we simply cannot see its surface with any clarity. Every observation is a compromise, a best guess based on incomplete data, which is why the scientific literature on Varuna is often filled with cautious language, wide error bars, and competing interpretations. The future of solving these mysteries, however, shines brightly on the horizon. The next generation of astronomical instruments promises to lift this veil in spectacular fashion. The James Webb Space Telescope, with its colossal mirror and unprecedented sensitivity in the infrared, is already turning its gaze toward the outer solar system. Its powerful spectrographs may finally be able to sniff out the faint spectral fingerprints of those elusive surface ices and any potential atmospheric gases, settling the composition debates once and for all. Here on Earth, the forthcoming extremely large telescopes with mirrors spanning 30 to 40 meters will gather light with a voracious appetite, allowing for photometric studies of stunning precision that could finally map the subtle asymmetries of Varuna's light curve and model its true shape with confidence. The ultimate dream, of course, is a dedicated spacecraft mission. While no such mission is currently planned, the concept of sending a probe to the Kuiper Belt to rendezvous with an object like Varuna is a compelling one for planetary scientists. A flyby mission, similar to New Horizons' visit to Pluto, would revolutionize our understanding. It would provide a direct, high-resolution image of its elongated shape, map the contrast between its dark plains and any bright icy patches, and directly sample its environment for any trace of an atmosphere. It would measure its mass with pinpoint accuracy by tracking the spacecraft's orbit, finally allowing us to calculate its density without ambiguity and unlock the secrets of its internal structure. For now, Varuna remains a tantalizing enigma, a world whose truths are held just beyond the reach of our current grasp, a reminder that the greatest discoveries in the outer solar system still lie ahead, waiting for the next leap in our ability to explore. But the story of Varuna does not end with its current, looping path through the outer darkness. It is a world in motion, not just spinning on its axis, but caught in the grand, slow-motion gravitational currents of the solar system. Looking forward across millions, even billions of years, we are faced with a final, profound mystery. What will ultimately become of this distant wanderer? The future of Varuna is not written in stone, but in gravity, and its long-term fate hinges on a delicate and unpredictable celestial dance with the giant planets. A dance that could see it become a different kind of object entirely, or even cast it out into the lonely void of interstellar space. One of the most likely futures for Varuna is a dramatic inward migration, transforming it from a denizen of the Kuiper Belt into a centaur object. The centaurs are a population of unstable icy bodies that orbit between Jupiter and Neptune, and they are widely understood to be refugees from the Kuiper Belt. Their orbits are chaotic and short-lived on cosmic timescales, often lasting only a few million years before they are flung elsewhere. This transition happens through gradual gravitational perturbations. Over countless orbits, the subtle, cumulative tug of Neptune's gravity can slowly but surely nudge an object like Varuna. Each close encounter, even a distant one, acts like a gentle push, gradually lowering the perihelion of its orbit, the point where it is closest to the Sun. Over millions of years, this process could pull Varuna's entire orbit inward, bringing it into the realm of the giant planets. If its perihelion drops below Neptune's orbit, its classification would change. It would shed its identity as a trans-Neptunian object and be reborn as a centaur, a much larger cousin to well-known bodies like Chiron or Chariklo. This new chapter would be far more violent and fleeting than its current stable existence. The region between Jupiter and Neptune is a gravitational maelstrom, a cosmic pinball machine where the immense gravity of the giant planets ruthlessly dominates. As a centaur, Varuna's orbit would become highly unstable and unpredictable. A close pass by Saturn or Jupiter could give it a colossal gravitational kick, radically altering its path in an instant. The possibilities from there branch into several dramatic pathways. It could be flung back outward to the Kuiper Belt, its journey reset. It could be hurled inward into the realm of the terrestrial planets, becoming a truly gigantic comet whose close approach to the Sun would trigger spectacular outbursts of activity as its volatile ices vaporized. Or its path could intersect with one of the giant planets themselves, leading to a final, catastrophic impact or a breakup into a ring system. A fate similar to what we believe happened to the object that created Saturn's rings. There exists another, even more final destiny, complete ejection from the solar system. This is often the ultimate fate for objects that venture too deep into the gravitational well of the giant planets. The mechanics of this are a masterpiece of orbital energy transfer. During a close encounter with a planet like Jupiter, an object can gain a tremendous amount of kinetic energy in a gravitational slingshot maneuver. If the geometry is just right, this energy boost can be enough to exceed the Sun's escape velocity. In this scenario, Varuna would not be scattered inward or outward, but would be flung entirely out of the solar system, its path bending into an open-ended hyperbolic trajectory. It would become a rogue planet, a lone wanderer drifting silently between the stars, its internal heat slowly fading over eons until it was little more than a frozen, dark tomb in the interstellar void. This is not a rare fate. Astronomers estimate that billions of such icy worlds have been ejected over the solar system's history, and Varuna could one day join their number. The timeline for these events is almost unimaginably vast. The gravitational influences that will dictate Varuna's future are subtle, operating on timescales of tens of millions of years. Its current orbit, while eccentric, appears stable for the foreseeable future, but foreseeable in human terms is a blink of an eye in cosmic time. The solar system is not a static clockwork mechanism. It is a dynamic, evolving system where tiny perturbations can snowball into dramatic changes over astronomical epochs. Predicting Varuna's exact path is impossible due to the inherent chaos of the n-body gravitational problem. We can run sophisticated computer simulations, but they show that its fate is exquisitely sensitive to initial conditions we cannot measure with perfect precision. A difference of a few kilometers in its position a million years from now could be the difference between remaining a Kuiper Belt object and being ejected into the galaxy. This long-term instability is not unique to Varuna. It is a fundamental property of the entire scattered disk population. These objects are the ones that felt the strongest gravitational kicks from Neptune's migration, and they inhabit the most precarious orbits in the outer solar system. By studying the possible future trajectories of a world like Varuna, we are actually studying the eventual dismantling of the Kuiper Belt itself. Over the next several billion years, as the Sun evolves and the planets continue their slow gravitational dance, the vast majority of these scattered objects will be cleared out, either ejected into interstellar space consumed by the Sun, or hurled into the inner solar system to meet their end. Varuna's future evolution mystery is therefore a microcosm of a grander process, a single thread in the tapestry of the solar system's long-term evolution, reminding us that even the most distant and seemingly permanent structures are ultimately transient in the face of gravity's relentless influence. So after this journey to the edge of our understanding, what are we left with? We are left with 25 profound mysteries, each one a thread in the tapestry of a world that defies simple explanation. From the cosmic roller coaster of its wild, eccentric orbit to its inexplicably rapid, dizzying spin, from the profound darkness of its tholin-coated surface to the baffling absence of any detectable atmosphere, we have the contradictory puzzle of its density, the distorted shape of a potential ellipsoid, and the thermal anomaly of its surprisingly warm interior. Its surface composition presents a chemical fingerprint with unexplained features, while its unpredictable light curve hints at a dynamic and changing world. We grapple with its unknown origins, questioning if it is a native of the Kuiper Belt, an immigrant scattered by Neptune, or even a captured interstellar vagabond. The question of its orbital resonance with Neptune remains open, and its confounding loneliness, the utter lack of any moons, sets it apart from its peers. Its distinct reddish hue speaks of complex chemistry, while the ongoing controversy over its very size prevents us from even classifying it with certainty. We see the potential for slow-motion seasons driven by its extreme orbit, and we trace its entire history back to a likely cataclysmic impact. The subtle asymmetries in its light curve whisper of giant basins and stark terrain contrasts, while the relentless weathering by cosmic rays has patiently painted its surface for billions of years. Its internal structure could be a simple primordial mix or a differentiated world with a rocky core and a potential subsurface ocean, and its place within the dynamical families of the Kuiper Belt remains ambiguous. Most importantly, Varuna serves as a pristine time capsule, holding clues to the conditions of the primordial solar system. Yet observing it from Earth remains a monumental challenge, pushing our technology to its absolute limits. And finally, we are left to wonder about its ultimate fate, whether it will remain in the dark, migrate inward, or be ejected into the galactic void. Each one of these 25 mysteries is more than just a gap in a textbook. It represents a vibrant opportunity for discovery, a frontier of knowledge waiting for the next generation of scientists and explorers. Collectively, they hold up a mirror to our own understanding, revealing just how much we still have to learn about the dark, cold, and astonishingly dynamic frontier of our own solar system. The puzzles of Varuna are a humbling and thrilling reminder that exploration is far from over. The next great leaps in understanding will come from the eyes of new telescopes like the James Webb Space Telescope, whose infrared gaze is already probing these distant worlds, and from the promise of future dedicated missions, spacecraft that could one day journey to this enigmatic world to see it not as a flickering point of light, but as a complex geological world. These are the endeavors that will transform these mysteries into understanding, continuing the greatest story ever told, the story of our cosmic home and its most distant, mysterious inhabitants.